Okay, so today we're going to talk about the orbital or angular momentum, and I warn you, this is going to be a lot of fun, and it's also something which is quite important. So here, all this part I will call the number one. Folks, just a little preparation for you guys. Could you guys add preparation? Like this. Okay, just prepare you guys for this. This was the last notes that I show you. Now, what is the key message here, which is on this board, and I'm going to show you what actually is quite important. This is have great importance here, and here's what I'm going to show you. Lx hat, Ly hat. These two are not commutable. They're not commutable. In the sense that they're not equal to 0. So therefore, there's no relationship between the eigen functions themselves. So there's no relationship. This, in turns out, it equals IH bar LZ. So this was the first place you will realize, and we will prove this already in the book. I'm not going to do it here. But I want to show you is that these two are not commutable. But now if you have Ly, Lz, these two also not commutable. Did you see how I remember this? Y, Z, X. X, Y, Z. Always this iteration. So similar like this. If I have Lz, Lx, IH bar, what I will get here? Well, Z, X, and what I will get here? Y, exactly. So this is what we get Y. And these are so-called very basic permutations. And that's a, now, become this, when you try to measure Lx, Ly simultaneously, Lx, then what will happen, you cannot measure them most accurately. You cannot. It won't be accurate to measure them. So they are not commutable. This is the uncertainty principle determined. Now, we cannot measure any pair accurately. So we cannot measure any pair accurately. So this is basically, if you want to measure this, you cannot measure this accurately. If you want to measure both of these, so you cannot do this because this is due to the uncertainty principle. So therefore, they do not share the common eigenfunctions. So they do not share the common functions. The common function, they won't have a common function available. So for these pairs, so that is not possible. In other words, what I just basically said was that everything that you learned here is useless for these functions. Basically useless. You cannot use it. And then what is useful now is this line underneath it. And this part of what becomes useful. And I want to change a different pen. This pen is a little bit of faint. So what you're going to see me write down is the bottom ones here. And the bottom one here is L squared, Lz. They are zeros. They are zeros. So the top one just shows you the very beautiful relation, but there you cannot use it. But this guy there equals 0. You also will find L hat Ly, this equals 0. And L hat Lx equals 0. So this essentially what it just said is that each of these components not commutable, so you cannot use it. But this part, we can use them. And this is the starting point, which you're going to see me. We're going to work on this guy's first, and then these two second. So in other words, you're going to see, you can follow me directly. You're going to see me, I'm going to solve for Lz first, and then Lx, Ly, and then get L squared. So that's the logic. I'm going to show you the logic here. So you're going to see me the logic like this, and you can see me logic like this. So logic like this. So there's so this way you can easily follow me what will happen in this case. So now we're going to show you one at a time what we're going to do. So this is essentially just preparation of these operators. So now next item, which we will do, is just try to calculate the different part of the operator with eigenfunctions. So this is eigenfunction starts here. So now we're going to talk about LZ, the eigenfunctions. So that's item number 1, item number 2, LZ. So we will deal with the LZs. But if you look at the LZ, it looks scary. Look at this. Sorry, the back. This equation looks scary. So even the LZ, we won't be able to do it in a Cartesian coordinate. We will do it in the spherical coordinates. So that's the key. Because if you're in the Cartesian coordinates, you can see here's x, y. So along all these directions, it's basically impossible. I'm going to show you what will happen like this. So this is my z-axis. Here's my y. And here's x, and then there's a y-axis. This LZ, you can notice that this LZ only have a component, it's either x or y. In other words, in the xy plane. Everything will be in the xy plane. It turns out, if you write the spherical coordinates, this LZ is extremely simple. It's just this operator. How simple it is? It's just partial over partial phi. Phi is the angle in the xy plane. So that's my phi angle. It's nothing to do with wave function. Wave function, we usually use phi, but this is just spherical coordinates. There's phi involved. So that's the one which we are going to show. And this phi itself is as a neutral angle. So the phi itself is the azimuthal angle, so that's why we will be able to use it. So our goal now becomes simple. We want to find a function which I use letter eta to represent that. So in other words, we're looking for the eigenfunction of LZ operator. Now equal, there's some number in front of it. I call it C. Sometimes in the book I use a lambda, but both are okay. They are similar in this fashion. So we're looking for now the eigenfunction of LZ. So this eigenfunction of LZ, that's what we're looking for. So in other words, the eta is unknown. So this is the one we are going to solve for that. Let me write this out completely. This will be mine. Minus IH bar partial phi over eta equals C phi. Now I said eta is only dependent on the phi itself. So in other words, if eta depends on phi itself, if eta depends on the phi itself, then we can change this one to a regular differential equation. Instead of a partial, we just use the d now, and this will be d phi is equal to c in like this. So that's the function which we have. And this differential equation can be solved easily. I'm going to both sides divide by eta, both sides times d phi. So I will have IH bar d eta over eta equals c d phi. And this is a rather straightforward. Both sides divide by IH bar. IH bar. So IH bar cancels out. So I get a logarithmic comes out. And our coefficient is called A. Doesn't matter what you get, but it's coefficient of A. And e to the negative. So sorry, this part should be like that. This will be positive now. So C IH bar and phi, like this. So I integrate over, and so this one becomes, I can move this I into the numerator. In the beginning, I have a negative I in the denominator. When I move to the numerator, I get a positive number. So then my eta just equals eta 0 e to the I. I don't know how to say it. Forgive me, folks. Let's remove this. This a is nothing here. It's just an integration over. And then what I have is e to the ch bar phi. And this is a function which we got over here. Okay. So integration, I hope you guys follows me, right? So this integration from here to there, that's logarithmic. That's d eta over eta, that's logarithmic, it makes sense. And then this where d phi just becomes phi. Doing good. Okay.
This is a really dumb question.
Sure.
How did you jump your I from the denominator to the numerator?
I will show you.
It's a simple trick.
Sure. Let me show you here. In the beginning, I have a denominator, negative I here. And then on top, I will have a 1, right? Now what I do, on top, I multiply by I, bottom by I.
Okay.
You got it? So therefore, I jump to the top. So that's what you get over there. It's a great question, though. So we get this equation. In other words, you see we found eigenfunction easily. So that's our eigenfunction. We need to fix this eta, though. So we need to fix this eta. Because we need to find out the entire expression. So in order to fix eta, so what we all do, we do the following here. Essentially, in order to fix eta, we need boundary conditions, as we did in the ENM case, similarly in this fashion. So there's nothing magic about this. So that is what my plan is, and I'm going to show you here now. So this is the eigenfunction of eta. So then I would like to do now. So I need to fix this. So now next step, we're going to use a boundary condition. Oh, sorry. Boundary condition. So this is the boundary condition. It stops. So this is the boundary condition. It's where the physics come into play. So our boundary condition for the atom, for all the atoms, it has spherical symmetry. For all the atoms, it has spherical symmetry. So it is completely spherical. So therefore, the atoms are spherical. So this means my eta, after our rotation by 2 pi, should come back to the original wave function. Original function, in other words, like this. Because it has spherical symmetry, you see on the azimuthal angle, if I rotate 360 degrees, 2 pi's, it shouldn't go back to the original one. Now I'm going to plug this relation to over here. On the left-hand side, what you have eta e to the I c h bar. This phi becomes phi plus 2 pi. So that is my left-hand side. So phi becomes phi plus 2 pi. Right-hand side is the original function. It's right like this. So that's the original function. So I'm going to cancel these coefficients. This term can be canceled out. All these 5 terms can be canceled out. So what I have is e to the I c 2 pi h bar equals 1. Okay. Are we good so far? In other words, I just want to make sure you guys follow me here. So all these 5 terms are exactly the same. So therefore, I can cancel this out. So the only term that remains is just this 2 pi, and equals that one. And this is in comparison with the 2n pi. So this will be in comparison with 2n pi equals 1. If I have 2n pi equals 1, and then this relationship is still valid. So this is the one which I'm going to use now. Check. Yes. In in the textbook, folks, did you see I use n here? Let's use n. I have a purpose for this. Of course, doesn't matter. It's all integers. I like this, all integers. So these two relations should be exactly the same. So therefore, the coefficient, the sort of exponents must be exactly the same, right? Makes sense? Exactly the same. So therefore, my c 2 pi over h bar has to equals m like this. Does that make sense to all of you? So in other words, so this will be, because this equals 1, this also equals 1, so the exponent must be the same. Don't be with me so far, right?
Where did the 2m pi term come from?
This 2 pi?
No, up one.
This 2 pi?
Yeah. Where did that term come from?
This term is use the identity. Let me show you why it must be the case. Let's put m equals 0. If m equals 0, Toby, you can see here e to the 0, so just 1, makes sense? If m equals 1, then I have a I2 pi, right? So I2 pi also equals 1. If m equals 2, same deal. 3, same deal. 4, same deal. Even plus minus, same deal. Plus minus, same deal. Doesn't matter, right? So therefore, this is identity. So usually the left-hand side and the right-hand side must be exactly the same. So then when I compare this generic expression with what I had before, and I have this relationship. Make sense? So now I can do a little cancellation. 2 pi cancels out. So then my C just equals n h bar. So eigenvalue, this is eigenvalue of LZ. I'm going to write it on the top. This is so important. So this is so important. And I'm going to write it over here. So in other words, I know how large C it will be. So I will LZ eta of C equals m h bar eta. So this is the one that I just used. Now you may wonder, Dr. Shen, why you use m? Well, this is called a magnetic. Could you guys write this down? Magnetic quantum number. It takes 0, plus minus 1, plus minus 2, and plus minus 3 until a number, here's a limit. Folks, it's not go to infinite, it has a limit, and I will tell you where the limit is. So for the moment, just remember the 0 plus minus 1 plus minus 2 plus minus 3, and there's a limit. So there's a limit, and which we will explain once we deal with these total angular momentum. So this is the limits which I'm going to explain to you, and so you're going to see. It's not completely obvious for the moment why it must have limits, but soon you will see them. So now we got the eigenfunction. Now did you see we have a eta 0 here? Did you see we have eta 0 here? We need to fix this guy. So what we do, how to fix eta 0? Alex, how do we fix eta 0? We have a wave function. These coefficients are all known now. How do we fix eta 0?
Just plug it.
No, you plug in here doesn't make any difference, because if you plug it in, you still have eta 0. Eta 0 does not allow you to calculate eta 0. Aisha, how do we get eta 0? This coefficient. Let me give you a little hint. I would start with n. Exactly. Did you hear it? Normalization. So we use a normalization as a way to fix this coefficient. Alex, it makes sense to you? So this is how your normalization works. So essentially what I will have, I have eta star, and this is the complex conjugation of the wave function, and d phi like this. Tobin, in this case, this symbol is exactly this symbol. Now I can use direct notation. This is a direct notation. Now you have integrals. So now you get familiar with this. These are multiple of each other, but with your brackets, you implicitly say there's an integration. And we say this guy equals 1. So this guy equals 1. So then you can see the first one will be eta 0. And this will be e to the negative I. My c is m now, and h bar. So h bar cancels out. It's m5. I hope I jumped a little bit. I hope you guys followed me. In the beginning, I have a c here, because this c is divided by h bar cancels out, so I have only m remains. And then the second term is also eta 0. This is a positive m5. d5 equals 1. Now these can be canceled out, and this will be n squared d5 equals 1. Integration over d5. How large, Alex, this is going to be? In how large?
Should just be 5.
Is it 5 or 2 pi?
5, but after doing the bounds, it'll be 2 pi.
Yeah, it should be 2 pi, right? Because it starts 0 here and all the way rotate over there, so this will be 2 pi. And now this guy will be eta 0, 2 pi equals 1. So my eta 0 just square root 2 pi. So then my entire wave function is dead. So this is I got everything that I need. So this is the wave function. So my final wave function I'm going to write over here. So my final wave function phi just equal 1 over square root 2 pi e to the I n phi. And this is the eigenfunction of the LZ. So in other words, this eigenfunction will be shared by the L squared itself. So you see, we'll peel off some portion of that off. That makes sense to all of you. So this is our eigenfunction for the LZ. Now, once we got any questions? Yes.
So when you go to do the normalization, are you just treating it not as your like normalization coefficient factor?
Yes, correct. Yes, exactly. It's just unknown at this step. Only after I stop equal to 1, then L eta 0 becomes known. Exactly. Yes. Your understanding is perfect here. There's no question about this. So this is how do we get there. All right. Now so once we're done with this, now the situation becomes much simpler. Essentially, because we now have the results. Some part of the wave, some part of eigenfunction of L squared is got. So this will be the L squared like this. To the L eigenfunction. So L squared eigenfunction. Now we are able to formulate this one. And I just want to. I tried different ways to explain this to you, but it turns out the simplest one method would be just follow the textbook. It's much simpler. And I want to give the message across, and then later I will show you what this is actually all about. So this is the one that I want to show you now. So this is the eigenfunction of the L squared. So the eigenfunction of L squared, we use a different name. We call it spherical harmonics. The eigenfunction of L squared is the spherical harmonics. So here the spherical, it means spherical coordinates. So this is called a spherical coordinates. So that's why we call it spherical in this case. The harmonics, it just means that we use the phi and the theta as a variables. So these are the variables. As a variables. That's called harmonics. The sine, cosine, these are harmonics that will be involved in this case. The spherical harmonics we represent by y. And if you read some of older European textbooks, they use different letters, but now commonly use the letter y to representing that. Underneath of it, we have two subscripts. One is called L. This L is orbital angular momentum. Sorry, first time I write this down completely. Quantum number. The L is called orbital angular momentum quantum number. This is the magnetic orbital momentum quantum number. And folks, now you can add this part on the top. Could you guys add the limit? The limits now we know it's limited by L. So we'll be in the end with plus minus L. I haven't derived how we calculate this, but don't worry, we will do that shortly. And then the subscript will be n. So we use n. So that's the entire the eigenfunction. So then we write out theta and phi in this fashion. So that is remember, we did not solve for this yet. We did not solve for this for the moment. We do not know how to solve for this, but you can see. So inside of this guy, inside this one, it must have some relationship close to this one here. So it must be because they're commonly shared. It turns out, I'm going to write this equation down here. And I'm not going to write out theta phi. It's implicitly included. This is going to equals the eigenfunction of the theta. I don't know what it looks like. I just use a block. So just show you. I don't know what that is. Just use the box. Okay. But now my eta, my phi, this is the known. It's a phi like this. So this I don't know, but this I do know. And I want to show you where you can find this. This in the textbook, if you have textbook, page 106, table 4.1. Let's look at this one. I don't know whether electronic version, probably fewer pages, I guess. Folks, let's go to page 106, everybody. And table 4.1. Table 4.1, and that will be there. Are you, which page that is? Alex, did you find it? Table 4.1. Table 4.1. Physical book is much easier. You can open it immediately. Did you find it? Table 4.1?
Yeah.
Find it? What about Alex? Did you find it? All right.
Page 61.
Page 61. Yeah. Okay, very good. Page 61, and so you see the column YM. Did you check? Could you check the e to the positive negative I phi? Did you see that? The first line. Second line is e to the positive negative I h phi. But now the last line, did you see here? E to the positive negative 2 I m I phi. Did you see that? Toby, did you see it? Did you see it? So I was talking about this one here. I don't want you to get lost. Here. These ones. Yeah, these ones. Did you see the middle column? The middle column have, so in other words, you can see the middle column there have this particular phi itself, the eta itself. So in other words, that's what it means, share the common eigenfunction. So they share the common, so this portion is the same. But now this part is nothing to do with LZ, because LZ has no theta dependence. So you will see our next job is try to find how to get this one out. So this is, but before we do that, I want to show you what's the consequence of this. If my L equals 0, this corresponds to all the s orbitals. So this is the chemistry. So L equals 0, this corresponds to the S orbitals. Did you know the S orbitals from chemistry class? S orbitals. So now if L equals 1, this is our p orbitals. So p orbitals like that. If L equals 2, this is our d orbitals like this. Now if you have a px, py orbitals, what you do, you will have m equals 0 plus minus 1. So for instance, let me erase the bottom line, so just want to make sure. If I have the pyz orbitals, so if I have a pz orbitals, then m equals 0. Px orbitals, m equals 1. Py, m equals -1. That's why the so-called magnetic quantum number is just allowed you to distinguish these three different p orbitals. Sometimes the quantum number 1 these two terms can be swapped. So that's why sometimes they do not specify whether you got m1, m equals 1 is a py or px. It doesn't matter because they're just completely equivalent. So this is a term that I have. Any questions? Any questions on this one? So now once we're done with this, and now we're going to show you, in other words, in the next step, you will see I'm going to completely get rid of this eta phi. In the equation, there will be no eta phi anymore, all right? Because it's already known. So then you will see only thing that we focus on the theta itself. So once they're done with theta, and that's our final job, which we will do. So essentially, you're going to see me write down everything what we are doing here is always focus on the theta part. So I want to have another line here. So wait, my eraser here, eraser. And this is the item number, should be line number 4 here. So I want to show you this, how do we get the theta part? When we're writing this part, we will struggle by the fact that many books just simply use a still mathematical ways to do it. So now we are going to show you, we are looking for theta part of LZ. So like this, that's the theta part. Just that way of my way of doing things, it's just like I want to show you how this part will be found out. So this is our job now. So we have two ways to do that. Way number 1, we solve LZ hat squared y Ln equals lambda. Lambda is eigenvalue of L squared, Ln. And this, it turns out, it's very difficult. Because this is essentially, you will get the Legendre polynomial. You can directly solve for this, express the LC in terms of these operators you can solve, but this is going to be very difficult. Even we already peel off that phi there. Way number 2, this is what we are using. So way number 2, we'll use L plus and L minus. It turns out this is easier. Of course, the results stay the same. There is no difference whatsoever there. So, but the next one is actually much simpler in this way. So it consists of 2 steps, and I'm not going to go over the time because instead I want you to look at it, read the textbook together. Let's go to page 104. Page 104. Page 104, start with equation 4.3.11. Folks, let's start with equation 4.3.11. So that's equation which we will start. We'll read this thing together quickly. Truman, could you read the first paragraph just before equation 4.3. On page 104.
In the harmonic oscillator, the ladder operators enabled us to find a series of eigenfunctions. Here an identical method is used. the raising and lowering operators L plus and L minus are constructed from Lx and Ly equations 4.3.3 and 4.3.5.
Okay, thank you. So in other words, the bottom equation is basically we consist like this. And Alex, could you read the next page, starting with where L underscore minus 1, L underscore plus, and equal, yeah, keep on going like that. Did you see it? Just the first line, first paragraph before, below 4.3.11.
Where L.
Exactly, yes, great.
Where L hat minus equals the dagger, L hat dagger plus, because the commutation of L sub x and L squared equals 0, commutation of L sub y and L squared equals 0, and the commutation of L plus or minus equals L squared equals 0. L plus or minus equals L squared. No. L plus or minus and L squared share the same eigenfunction, that of YLM equals G theta beta 5 is an eigenfunction of L squared, that L plus YLM and L minus YLM are also eigenfunctions of L squared. This key relationship used to find G theta, however, harmonic oscillator do not know what L plus YLM or L minus YLM produces, so we cannot find the equation by conclusion. 3.2.12, we need help from L sub z, we apply L sub
Okay,
z.
yeah, stop here. Thank you very much. Okay, any question on this shorter paragraph? Any questions? Any questions? Yeah, think about it. This paragraph is very dense. Any question on this? Aisha, any questions? Yes, Toby, please.
When it says to apply the LZL plus to the YLN, is LZL plus known for like this case, and that's why we're doing that?
LC plus L plus you mean talking
Yeah, when it says you apply L.
Oh no, we're not there yet. We're just on this paragraph first. Yeah.
I see.
Yeah. Okay, here's a question I want to ask you guys. Did you see in the book it says L plus Y LM, L minus Y LM are also eigenfunctions of L dagger. In other words, we know this guy assumed is eigenfunction of L squared. But why this operator applied to this is also eigenfunction of L squared. Doesn't make sense to you? Do you understand my question? My question, I know y itself is an eigenfunction of L squared. Perfect. But why this guy applied to this whole thing is also an eigenfunction of L squared.
Is L plus a ladder operator in a way?
Yeah, it is allowed. Yeah, it is allowed.
No, is it a ladder operator?
Yes, it's just like a ladder operator. Yes, it's a ladder operator. Yes.
As if they're the same. Do they equal each other?
Exactly. Did you hear it? Because L hat. Well, could you guys write this down? This is a really important, most important moment now for this class. This is because, watch carefully. This is because L plus L squared, these two are permutable. If they're not permutable, sorry, you cannot do that. And this is the most important thing we need to emphasize. This is the most important. Because they are permutable, if they're not permutable, because if you basically applied an operator onto a function, you said, well, this is originally it's the eigenfunction, but when you apply the operator on this function, it's still the eigenfunction of what you had before. Token, did you see what I mean here? Did you see what I mean? You know, the y, even though the y itself is an eigenfunction, which is obvious, but why this operator apply this and it's still eigenfunction of this? That's the question. You see, that is a challenge. This eigenfunction is perfect, but why you apply an operator on this still eigenfunction? That's not obvious. You can plug any operator on the top, it may not be anywhere. So that's what I mean here. The main reason is these two are permutable. Same thing here. These are permutable. So each sentence when we were writing this part, some folks just skim over and they say, well, you probably see what take, but just keep on asking those questions. Okay, sounds good? All right, so we're going to end it here. Any other questions? We just ask me later. All right, sounds good. I'm going to stop the recording. Sorry, because my